In computer programming, a return statement causes execution to leave the current subroutine and resume at the point in the code immediately after where the subroutine was called, known as its return address. The return address is saved, usually on the process's call stack, as part of the operation of making the subroutine call. Return statements in many languages allow a function to specify a return value to be passed back to the code that called the function. Overview: in C++, return exp is a statement that tells a function to return execution of the program to the calling function, and report the value of exp. If a function has the return type void, the return statement can be used without a value, in which case the program just breaks out of the current function and returns to the calling one. In Pascal there is no return statement. A subroutine automatically returns when execution reaches its last executable statement. Values may be returned by assigning to an identifier that has the same name as the subroutine, a function in Pascal terminology. This way the function identifier is used for recursive calls and as result holder. This is syntactically similar to an explicit output parameter. The same syntax is used in Fortran 66 and Fortran 77. In some other languages a user-defined result variable is used instead of the function identifier. Oberon has a return clause instead of a return statement. The return clause is placed after the last statement of the procedure body. This enables compile-time checking of proper return and return value from the procedure. Some expression-oriented programming language, such as Lisp, Perl and Ruby, allow the programmer to omit an explicit return statement, specifying instead that the last evaluated expression is the return value of the subroutine. In other cases a null value is returned if there is no explicit return statement. In Python, the value none is returned when the return statement is omitted, while in JavaScript the value undefined is returned. In Windows PowerShell all evaluated expressions which are not captured are returned from the subroutine as elements in an array, or as a single object in the case that only one object has not been captured. In Perl, a return value or values of a subroutine can depend on the context in which it was called. The most fundamental distinction is a scalar context where the calling code expects one value, a list context where the calling code expects a list of values and a void context where the calling code doesn't expect any return value at all. A subroutine can check the context using the wantArray function. A special syntax of return without arguments is used to return an undefined value in scalar context and an empty list in list context. The scalar context can be further divided into Boolean, number, string, and various reference types contexts. Also, a context-sensitive object can be returned using a contextual return sequence, with lazy evaluation of scalar values. Values returned by the program when it terminates are often captured by batch programs. Syntax: return statements come in many shapes. The following syntaxes are most common: multiple return statements. Languages with an explicit return statement create the possibility of multiple return statements in the same function. Whether or not that is a good thing is controversial. Strong adherents of structured programming make sure each function has a single entry and a single exit. It has thus been argued that one should eschew the use of the explicit return statement except at the textual end of a subroutine, considering that, when it is used to return early, it may suffer from the same sort of problems that arise for the GOTO statement. Conversely, it can be argued that using the return statement is worthwhile when the alternative is more convoluted code, such as deeper nesting, harming readability. In his 2004 textbook, David Watt writes that single-entry multi-exit control flows are often desirable. Using Tennant's framework notion of sequencer, Watt uniformly describes the control flow constructs found in contemporary programming languages and attempts to explain why certain types of sequencers are preferable to others in the context of multi-exit control flows. Watt writes that unrestricted GOTOs are bad because the destination of the jump is not self-explanatory to the reader of a program until the reader finds and examines the actual label or address that is the target of the jump. In contrast, Watt argues that the conceptual intent of a return sequencer is clear from its own context, without having to examine its destination. Furthermore, What writes that a class of sequences known as escape sequences, defined as sequencer that terminates execution of a textually enclosing command or procedure, encompasses both breaks from loops and return statements. What also notes that while jump sequences have been somewhat restricted in languages like C, where the target must be an inside the local block or an encompassing outer block, that restriction alone is not sufficient to make the intent of Gotos in C self-describing, and so they can still produce spaghetti code. What also examines how exception sequences differ from escape and jump sequences. For details on this, see the article on structured programming. According to empirical studies cited by Eric S. Roberts, student programmers had difficulty formulating correct solutions for several simple problems in a language like Pascal, which doesn't allow multiple exit points. For the problem of writing a function to linearly searching an element in an array, a 1980 study by Henry Shapiro found that using only the Pascal-provided control structures, the correct solution was given by only 20% of the subjects, while no subject wrote incorrect code for this problem if allowed to write a return from the middle of a loop. Others, including Kent Beck and Martin Fowler, argue that one or more guard clauses, conditional early exit return statements near the beginning of a function, often make a function easier to read than the alternative. The most common problem in early exit is that cleanup or final statements are not executed. For example, allocated memory is not unallocated, or open files are not closed, causing leaks. These must be done at each return site, which is brittle and can easily result in bugs. For instance, in later development, a return statement could be overlooked by a developer, and an action which should be performed at the end of a subroutine might not be performed in all cases. Languages without a return statement, such as standard Pascal, don't have this problem. Some languages, such as C++ and Python, employ concepts which allow actions to be performed automatically upon return, which mitigate some of these issues. These are often known as try-finally, or similar. Ironically, functionality like these finally clauses can be implemented by a goto to the single return point of the subroutine. An alternative solution is to use the normal stack unwinding at function exit to unallocate resources, such as fire destructors on local variables, or similar mechanisms such as Python's with statement. Some early implementations of languages such as the original Pascal and C restricted the types that can be returned by a function to simplify their compilers. In Java it is possible to execute code even after return statement, because the finally block of a try-catch structure is always executed. So if the return statement is placed somewhere within try or catch blocks, the code within finally will be executed. It is even possible to alter the return value of a non-primitive type because the exit occurs afterwards as well. Yield statements. Cousin to return statements are yield statements, where a return causes a subroutine to terminate, a yield causes a coroutine to suspend. The coroutine will later continue from where it suspended if it is called again. Coroutines are significantly more involved to implement than subroutines, and thus yield statements are less common than return statements, but they are found in a number of languages. See also, return type, exit status, references.